Hello everyone, my name is Ofayas and I'm doing PhD in organic chemistry at UNSW Sydney, Australia, and you are watching my YouTube channel which is named as Kemistry. It's not C for chemistry but K for chemistry. Just to let you know, if you are first time watching my channel or if you haven't watched my all videos on my YouTube channel, then you can have a look on my YouTube channel and you will find a number of playlists starting from spectroscopy, tutorials, retrosynthesis, natural products, and organic name reactions, spectroscopy including NMR, UV visible spectroscopy and IR spectroscopy, where I have uploaded several different kind of videos, such as one video is about how to write research papers, and one video is about how to apply for PhD admissions and scholarships, and one video is about how to write an effective email to a supervisor in order to get funding, or in order to get admission for PhD, in order to get a postdoc, or in order to apply for a visiting fellow. You should watch that video if you want to apply for these sort of purposes. But okay, now let's get back to our topic. So today topic is what is organic chemistry. Very simple topic, and I should have made this video first, but nevertheless I'm making this video for my channel and for you audience. And just to let you know that I am following organic chemistry textbook written by Clayden and co-authors. It's Clayden, it's not Clayden. Someone was hearing me that I'm saying it's Clayden, but it's not Clayden. It's a mispronunciation, or you might be hearing me wrong. I may sound to you that I'm mispronouncing, but the author name is Clayden, C-L-A-Y-D-E-N. Okay, Clayden. So if you need this book of organic chemistry, then drop down the email in my on the video below, then I'll try to email you the book. So what I'm doing, I'm taking exact lines from the book and then explaining them in for you guys. Okay, so next is organic chemistry and you. So this is the first topic of that chapter, and that is the chapter 1 of book of organic chemistry written by Clayden and co-authors. So topic is organic chemistry and you. You are already a highly skilled organic chemist. As you read these words, your eyes are using an organic compound. Okay, so there's an organic compound which is present in your eyes. As you are watching my video, your eyes contain an organic compound which is called retinal. What is the purpose of that compound? Is to convert visible light into nerve impulses. This is done through this compound. When you picked up this book, your muscles were doing chemical reactions on sugars to give you energy you needed. As you understand, gaps between your brain cells are being bridged by simple organic molecules that is called neurotransmitter amines, so that nerve impulses can be passed around your brain. And you did all that without consciously thinking about it. You do not yet understand these processes in your mind as well as you can carry them out in your brain and body. You are not alone there. No organic chemist, however brilliant, understands the detailed chemical working of the human mind or body very well. So, in order to summarize these lines in my own words, the author is trying to say that organic chemistry is heavily and deeply involved in the human body and human mind, and whatever we do, some sort of organic compounds or some sort of organic chemicals, they are helping us to perform the daily life tasks. So author is starting from a very simple molecule which is present in our eyes, that is called retinal, which helps us to see the things. And author is trying to explain that the energy that we require to perform different tasks comes from sugars that we intake through different foods, and the signals that our brain cells transfers to our body is taking place due to the organic compounds called neurotransmitter amines. So whether you think or whether you do not think, you are using organic chemistry in your whole daily life workings, as well as in thinking, as well as seeing the things. You are basically richly enriched with the organic compounds. You are not away from the organic chemistry, and you are not you cannot separate yourself from organic chemistry. We, the authors means authors of this book of organic chemistry, include ourselves in this generalization, but we are going to show you in this book what enormous strides have been taken in the understanding of organic chemistry since the science came into being in the early years of the 19th century. Organic chemistry began as a tentative attempt to understand the chemistry of life. So that is how organic chemistry started. So organic chemistry basically helps us to understand the chemistry of life. It has grown into the confident basis of vast multinational industries that feed, clothe, and cure millions of people without their even being aware of the role of chemistry in their lives. Chemists cooperate with physicists and mathematicians to understand how molecules behave, and with biologists to understand how molecules determine life processes. So organic chemistry plays a central role in daily life processes, in industry of food, in industry of clothing, and it also closely works with physics and mathematics, and it also closely works with biologists. The development of these ideas is already a revelation at the beginning of the 21st century, but is far from complete. We aim not to give you the measurements of the skeleton of a dead science, but to equip you to understand the conflicting demands of an adolescent one. Like all sciences, chemistry has a unique place in our pattern of understanding of the universe. It is the science of molecules, but organic chemistry is something more. It literally creates itself as it grows. Of course, we need to study the molecules of nature, both because they are interesting in their own right and because their functions are important to our lives. Organic chemistry often studies life by making new molecules that give information not available from the molecules actually present in living things. Here you can see, this is the structure of 11-cis retinal, absorbs light when we see. This is the molecule which is present in your eyes, in my eyes, in the eyes of everyone. And it is an organic compound. So, as you know that organic compounds comprise of different functional groups, it contains aldehyde group. This one is aldehyde, alkene, double bond, alkene, alkene, and alkene. So 1, 2, 3, 4, and 5 double bonds. And it also contains a ring, 6-member ring. And it also contains 1, 2, 3 methyl groups. So this is the structure of a molecule which is responsible for the vision of what we see. And it is present in the eyes of human beings. Next interesting molecule is serotonin. and it's a human neurotransmitter. It helps human brain cells to carry nerve impulses or carry messages from brain to tissues and all body organs. And the molecule that is responsible for this work is called serotonin. And again, if we look at the molecule, it contains primary amine, that is NH2, and it also contains OH group, but this is called phenol. This is the phenolic OH, and this is NH is a secondary amine and double bond. So these are the major functionalities present in the serotonin molecule, and once again it's an organic molecule. So we are going to give you structures of organic compounds in this chapter, otherwise it would be rather dull. If you do not understand the diagrams, do not worry, explanation is on its way. So these are the molecules which are present in human body along with so many other molecules. So this is just to highlight how big and how rich organic chemistry is, and how deeply involved organic chemistry is in performing all sorts of tasks for human body, for human mind. This creation of new molecules has given us new materials such as plastics, new dyes to color our clothes, like all the plastics involve organic molecules. All the dyes that you use to color your clothes or other stuff, they all involve organic compounds. New perfumes to wear, that you use perfumes on your clothes, they all also involve organic molecules. Every single medicine that has been still made today, till today, even the vaccine of coronavirus utilizes the organic molecules. Some people think that these activities are unnatural and their products dangerous or unwholesome, but these new molecules are built by humans from other molecules found on earth using skills inherent in our natural brains. Birds build nests, men make houses, which is unnatural. To the organic chemist, this is meaningless distinction. There are toxic compounds and nutritious ones, stable compounds and reactive ones, but there's only one type of chemistry. It goes on both inside our brains and bodies and also in our flasks and reactors, born from the ideas in our minds and the skill in our hands. That is organic chemistry, ladies and gentlemen. We are not going to set up ourselves as moral judges in any way. We believe it is right to try and understand the world about us as best we can and to use that understanding creatively. This is what we want to share with you. And let me tell you one thing. The Nobel laureate, Alfred Nobel, he created the Nobel Prize. He was an organic chemist. He introduced a dynamite bomb. So the dynamite bomb was sold so much and he got so much money from that, selling that compound, and he put that money in a bank. Now the interest on that money that is generated every year is distributed among the Nobel laureates, Nobel winners. So and one more thing, organic chemistry has won many Nobel Prizes compared to inorganic and physical chemistry. So the Nobel Prizes won in the area of chemistry major or in organic chemistry. Mostly are in organic chemistry. So organic chemistry is involved everywhere, my dear fellows. You cannot shy away from organic chemistry. Everything that you see, plastics, colors, dyes, medicines, drugs, they all are organic. Now let me clear one thing. Organic does not mean that comes from a natural resource. Organic means that contains a CH bonds. Chemistry of hydrocarbons and their derivatives is called organic chemistry. Compounds that contain CH bonds along with other heteroatoms, nitrogen, oxygen, sulfur, they all are organic. And up until today, millions of organic compounds have been synthesized and they've been utilized for so many elegant purposes. Life would have been less beautiful without organic compounds. That's what I can say. Life would have been dull without organic compounds. You might have died early. So many people have died early. There would have been no cure of so many diseases if there was no organic chemistry. Trust me, every single medicine that exists on planet Earth contains organic compounds. The most recent service of organic chemistry for humankind is that several organic compounds are taking part in the making of coronavirus vaccine. COVID-19 vaccine contains a number of organic compounds. That is the beauty of organic chemistry. You just cannot shy away from that organic chemistry. And who is the mother of organic chemistry? Nature. Nature is the mother of organic chemistry. So nature creates, nature gives birth to the organic compounds. You see a fish that contains 100,000 chemicals. You see a plant, you see a tree that contains 100 chemicals, more than 100 chemicals. You see a bird, you see an animal, they all contain wide variety of chemicals that we call as organic compounds. Okay, let's come back to the topic, that is organic compounds. So organic chemistry started as the chemistry of life, when that was thought to be different from the chemistry in the laboratory. Then it became the chemistry of carbon compounds, especially those found in coal. Now it is both. It is the chemistry of compounds of carbon along with other elements such as are found in living things and elsewhere. So before, in early stages or prior to 19th century, 18th century, organic chemistry was defined as a chemistry which is utilizes the natural sources, or it is believed that organic compounds can only be obtained from the natural source, and that theory was called VFT, vital force theory. And this theory stated that organic compounds cannot be synthesized in laboratory. They can only be obtained from a natural source, be it a plant, be it an animal, whatever it is, but it must be a natural source. That is how organic chemistry used to be defined. But then it changed. People define organic chemistry as study of carbon. Then people modified the definition as study of carbons and hydrocarbons. My dear friends, the petroleum products, the petrol that you use, the fuel that you are using in your cars, aeroplanes, trains, it is all organic. It all contains organic compounds. What more can I say? Think about it. Appreciate organic chemistry, man. What is organic chemistry? That is the chapter that we are discussing, and the book is Clayden, and that is the chapter 1. So the organic compounds available to us today are those present in living things and those formed over millions of years from dead things. In earlier times, the organic compounds known from nature were those in the essential oils that could be distilled from plants, and the alkaloids that could be extracted from crushed plants with acid. Menthol is a famous example of a flowering compound from the essential oil of spearmint, and cis jasmine an example of a perfume distilled from jasmine. And jasmine is a national flower of Pakistan, if you don't know it. So cis jasmine is a perfumery compound, has a fragrance, is obtained from a plant called jasmine flowers. Menthol, again, it's a very bioactive molecule obtained from plants. This is quinine, It's an alkaloid. It's also obtained and extracted from the plants. As I mentioned that all the plants contain several complex organic compounds. And it took years of effort and hard work of several organic chemists to identify, recognize, characterize, and elucidate and establish the structure of the molecules obtained from the plants as well as animal sources. Even in the 16th century, one alkaloid was famous. Quinine was extracted from the bark of South American cinchona tree and used to treat fevers, especially malaria. The Jesuits who did this work, the remedy was known as Jesuit's bark. Did not, of course, know what the structure of quinine was, but now we do. The main reservoir of chemicals available to the 19th century chemist was coal. Distillation of coal to give gas for lighting and heating, mainly hydrogen and carbon monoxide, also gave a brown tar rich in aromatic compounds such as benzene, pyridine, phenol, aniline, and thiophene. This is the structure of benzene, pyridine, phenol, aniline, thiophene. Phenol was used by Lister as an antiseptic in surgery, and aniline became the basis for the dye stuff in industry. It was this that really started the search for new organic compounds made by chemists rather than by nature. A dye stuff of this kind is still available, is Bismarck brown, which should tell you that much of this early work was done in Germany. Bismarck brown, why? So this is a dye which contains this azo group, and this is the NH2. This one is NH2 amine group, and this is the dye. This is called Bismarck brown Y dye. And now there are millions of organic compounds, so there are general formula for this. An enormous number length of molecules is n plus 2 carbon atoms. N is equals an enormous number of length of molecules is n plus 3 carbon atoms. In the 20th century, oil overtook coal as the main source of bulk organic compound, so that simple hydrocarbons such as methane, it's a compound which is present in natural gas, and propane, CH3, CH2, CH3, calor gas became available for fuel. At the same time, chemists began the search for new molecules from new sources such as fungi, corals, and bacteria, and two organic chemical industries developed in parallel: bulk and fine chemicals. Bulk chemicals like paints, plastics are usually based on simple molecules produced in multi-ton quantities, while fine chemicals such as drugs, perfumes, and flavoring materials are produced in smaller quantities but much more profitably. At the time of writing, there were about 16 million organic compounds known. How many more are possible? There is no limit. So when this book was written, 16 million organic compounds were known, and it has been several years passed by since this book has been written, and the number of organic compounds is kept increasing. There's no end to it. Imagine you have just made the longest hydrocarbon ever made. You just have to add another carbon atom and you have made another. This process can go on with any type of compound ad infinitum. But these millions of compounds are not just a long list of linear hydrocarbons. They embrace all kinds of molecules with amazingly varied properties. In this chapter, we offer a selection. What do they look like? They may be crystalline solids, oils. Organic compounds could be crystalline solids, oils, waxes, plastics, elastics, mobile or volatile liquids or gases. Familiar ones include white crystalline, that is a sugar. Sugar is an organic molecule. A cheap natural compound isolated from plants is hard white crystals when pure, and petrol, a mixture of colorless, volatile, flammable hydrocarbons. Isooctane is a typical example and gives its name to the octane rating of the petrol. So that's what we say, high octane petrol. Sucrose, that is a structure of ordinary sugar isolated from sugar cane or sugar beet, and its appearance is like white crystalline solid, and this is the structure of sucrose. This is the structure of isooctane, a major constituent of the petrol, volatile flammable liquid. The compounds need not lack color. Indeed, we can so on dream up a rainbow of organic compounds covering the whole spectrum, not to mention black and brown. In this table, we have avoided dye stuffs and have chosen compounds as varied in a structure as possible. Have a look at this table. Spectrum. So, S-P-E-C-T-R-U-M. And the S, we have a red color. For P, we have the orange. And E, yellow, green, blue, purple. Dark red hexagonal plates. Compound name is 3'-methoxy-benzocycloheptatri-2-on, and this is the structure of that molecule, which is red in color. Orange, amber needles, dichlorodicyanoquinone DDQ. This is the molecule which has orange color. Yellow, toxic yellow explosive gas, diazomethane. This is a very tiny molecule which is yellow in color. Green prisms with a steel blue luster, 9-nitroso-julolidine, that is a structure. Blue, deep blue liquid with a peppery smell, azulene, that is the structure of azulene. Purple, deep blue gas condensing to a purple solid, nitroso-trifluoromethane, that is the compound which is purple. So the point that authors are telling in this table is that organic compounds are rich in color as well. They could be of any color, you name it. They cover all of the spectrum of colors. Color is not the only characteristic by which we recognize compounds. All too often it is their odor, how they smell, that lets us know they are around. There are some quite foul organic compounds too. The smell of the skunk is a mixture of two thiols, sulfur compounds containing SH groups. So these are the very, very smelly compounds. The skunk spray contains these two compounds. Generally speaking, sulfur containing compounds are super bad smelly. But perhaps the worst aroma was that which caused the evacuation of the city of Freiburg in 1889. Attempts to make thioacetone by the cracking of trithioacetone gave rise to an offensive smell which spread rapidly over a great area of the town, causing fainting, vomiting, and a panic evacuation. The laboratory work was abandoned. That is the reaction that was going to take place. People were trying to make thioacetone from this trithioacetone, and the Freiburg was evacuated because of a smell from the distillation of this compound. Ha ha ha. Isn't it funny? It's not funny, man. It's super smelly compound. It was perhaps foolhardy for workers at an ESO research station to repeat the experiment of cracking trithioacetone south of Oxford in 1967. Let them take up the story. Recently we found ourselves with an odor problem beyond our worst expectations. During early experiments, a stopper jumped from a bottle of residues and, although replaced at once, resulted in an immediate complaint of nausea and sickness from colleagues working in a building 200 yards away. Two of our chemists, who had done no more than investigate the cracking of minute amounts of trithioacetone, found themselves the object of hostile stares in a restaurant and suffered the humiliation of having a waitress spray the area around them with a deodorant. The odors defied the expected effects of dilution, since workers in the laboratory did not find the odor intolerable, and genuinely denied responsibility since they were working in closed systems. To convince them otherwise, they were dispersed with other observers around the laboratory at distances up to a quarter of a mile, and one drop of either acetone, gem dithiol, or the mother liquors from crude trithioacetone crystallizations were placed on watch glass in a fume cupboard. The odor was detected downwind in seconds. This is the propane dithiol, and this is the 4-methyl-4-methylsulfane, two candidates for the worst smell in the world. No one wants to find the winner. The divine smell of the black truffle comes from this compound. Damascenone, the smell of roses, is because of this compound. Not all compounds smell bad. Some compounds smell beautiful. There are two candidates for this dreadful smell propane dithiol called acetone gem dithiol above, or 4-methyl-4-methylsulfane. It is unlikely that anyone else will be brave enough to resolve the controversy. Nasty smells have their uses. The natural gas piped to our homes contains small amounts of deliberately added sulfur compounds such as terbutylthiol. When we say smell, we mean very small. Humans can detect one part in parts of natural gas. Other compounds have delightful odors. To redeem the honor of sulfur compounds, we must cite the truffle, which pigs can smell through a meter of soil, and whose taste and smell is so delightful that truffles cost more than their weight in gold. Damascenone are responsible for the smell of roses. If you smell one drop, you will be disappointed, as it smells rather like turpentine or camphor. But next morning, you and the clothes you are wearing will smell powerfully of roses. Just like the compounds from trithioacetone, this smell develops on dilution. Humans are not the only creatures with a sense of smell. We can find mates using our eyes alone, though smell does play a part. But insects cannot do this. They are small in a crowded world, and they find others of their own species and the opposite sex by smell. Most insects produce volatile compounds that can be picked up by a potential mate in incredibly weak concentrations. Only 1.5 mg of serotonin, the sex pheromone of the cigarette beetle, could be isolated from 65,000 female beetles, so there isn't much in each beetle. Nevertheless, the slightest whiff of it causes the males to gather and attempt frenzied copulation. The sex pheromones of the Japanese beetle, also given off by the females, has been made by chemists. As little as 5 micrograms was more effective than 4 virgin females in attracting the males. Serotonin, this is the molecule, the sex pheromone of the cigarette beetle, Lesioderma sericorni. Japonilure, the sex pheromone of the Japanese beetle, Popillia japonica. The pheromone of the gypsy moth, Disparlure, was identified from a few micrograms isolated from the moths, and only 10 micrograms of synthetic material as little as 2 × 10⁻⁻12 gram is active as lure for the males in field tests. The 3 pheromones we have mentioned are available commercially for the specific trapping of these destructive insect pests. Don't suppose that the females always do all the work. Both male and female olive flies produce pheromones that attract the other sex. The remarkable thing is that one mirror image of the molecule attracts the males while the other attracts the females. Olein. Sex pheromone of the olive fly, Bacrocera olei. This mirror image isomer attracts the males. This mirror image isomer attracts the female. These ones. This is the Disparlure, the sex pheromone of the gypsy moth, Porphyria dispar. What about taste? Taking the grapefruit, the main flavor comes from another sulfur compound, and human beings can detect 2⁻10⁻5 parts per billion of this compound. This is an almost unimaginable small amount equal to 10⁻⁻4 mg per ton, or a drop, not in a bucket but in a good-sized lake. Flavoring principle of grapefruit. This is the compound which is responsible for the flavoring principle in grapefruit. For a nasty test, we should mention bittering agents put into dangerous household substances like toilet cleaner to stop children eating them by accident. Notice that this complex organic compound is actually a salt. It has positively charged nitrogen and negatively charged oxygen atoms, and this makes it soluble in water. That's the molecule. This is called Bitrex, a denatonium benzoate. So this is the negative and this is the positively charged molecule. Other organic compounds have strange effects on humans, like alcohol. People drink in tons. Various drugs such as alcohol and cocaine are taken. This is a cocaine structure. People who use drugs, they love this molecule, cocaine. They have their dangers. Too much alcohol leads to a lot of misery, and in cocaine, it all make you a slave for life. Again, let's not forget other creatures. Cats seem to be able to go to sleep at any time, and recently a compound was isolated from their cerebrospinal fluid of cats that makes them, or rats or humans, go off to sleep quickly. It is surprisingly simple compound. That is this one. A sleep-inducing fatty acid derivative cis-9,10-octa-decanomide. This is the compound which is responsible for the sleep in cats. This compound and dysparlure are both derivatives of fatty acids, molecules that feature in many of the food problems people are so interested in now, and rightly so. Fatty acids in the diet are a popular preoccupation, and the good and bad qualities of saturates, monosaturates and polyunsaturates are continually in the news. This too is organic chemistry. One of the latest molecules to be recognized as an anti-cancer agent in our diet is CLA, conjugated linoleic acid in dairy products. So this is the structure of that molecule, which contains 18 carbons, and it has been identified as anti-cancer agent in the dietary. There's a conjugated linoleic acid cis 9 trans 11. So the double bond at 9 position is cis and double bond at 11 is trans. Conjugated linoleic acid. That is the structure of that compound. Another fashionable molecule is reverse citral, which may be responsible for the beneficial effects of red wine and preventing heart disease. It is a quite different organic compound with 2 benzene rings, and you can read about it in chapter 51 of the Clayden book. So it contains this double bond, and it contains 1,3-diphenol, and also it contains the 4-hydroxyphenyl ring. For our third edible molecule, we choose vitamin C. This is an essential factor in our diets. Indeed, that is why it is called a vitamin. The disease scurvy, a degeneration of soft tissues, particularly in the mouth, from which sailors on long voyages like those of Columbus suffered, results if we don't have vitamin C. It also is a universal antioxidant, scavenging for rogue free radicals and so protecting us against cancer. Some people think an extra large intake protects us against the common cold, but this is not yet proved. So this is the structure of a vitamin C, and let me ask you a question that so many people ask: which among these OH groups is most acidic hydrogen? This one, or this one? If you don't know the answer, then go to my YouTube channel, where I have made a video in which I have mentioned that which of these 4 hydroxyl protons is more acidic in vitamin C and why. Vitamin C ascorbic acid is a vitamin for primates, guinea pigs and fruit bats, but other mammals can make it for themselves. This is the structure of vitamin C, and it's also called ascorbic acid. So this chapter is very long, and I'm following the Clayden book. So far I have covered so many things about organic chemistry. I hope after watching this video you have developed the interest in organic chemistry, and you have a journey that I have taken through from simple molecules, how big variety and diversity organic compounds they possess in different applications they involved in, and it's very intriguing and it's very exciting to study these molecules in order to understand the chemistry of life. And I would like to thank you guys for watching this video, and don't forget to subscribe and share link with your friends. See you with the next video. Take care. Bye.